up, everybody? It's Friday. Uh, Yoda's in the building. Baby Yoda, shout out. You will watch The Mandalorian because it's a fantastic show. CP Geometry today, 4.4 perpendicular lines. Let's just get right into it, guys. So, perpendicular lines. We've talking about parallel lines before. We talked about the different angle pair relationships, and now we're going to talk about perpendicular lines. Hopefully you have some idea of what a perpendicular line is, but basically perpendicular lines, and this will not look beautiful, but perpendicular lines meet at a 90-degree angle. So parallel lines run side by side, they're equidistant, they never touch. Perpendicular lines touch once and they cross at a 90-degree angle. So essential question, what are the key ideas about perpendicular bisectors of a segment? That is the point. Now this first part is construction. You guys, we know we usually typically pass over these. If you want to find an activity online, you can probably just type in perpendicular bisector construction, or if you really want one, I can look. We're not going to do that right now. So moving right along to explain one. So proving the perpendicular bisector theorem using reflection. So you guys need to realize that everything we're doing tends to build on each other. So please make sure that you are, not forgetting about the past lessons, the past modules, because they are building blocks going forward, and I hope you're realizing that now. So make sure your notes are nice and clean. If not, go back and do something about it. So the perpendicular bisector theorem states if a point is on the perpendicular bisector of a segment, so you got to know what a perpendicular bisector is, you got to know what a point is, a segment, then it is, so if and then statement, if P then Q, then it is equidistant from the endpoints of the segment. If you don't know what equidistant means, look at the words, equal distance. So it has the same distance from the endpoints of the segment. So let's prove the perpendicular bisector theorem. Well, consider the reflection, let me change my color, across line M. Then the reflection of point P across line M is also P, because P lies on line M, though too many words. So if you reflect this across this line M right here, it's not going to go anywhere. It's going to end up right there. It's not moving. Also, the point of reflection, the reflection of point A across line M would end up being point B, right? Do you see these little tick marks? These show you that they're equidistant here. So if you reflected A across line M, you'd end up over there where point B is. Therefore, PA equals PB because reflection preserves distance as it is a rigid motion. So PA, let me use a different color, is equivalent to PB. Cool? Cool. That proves the perpendicular bisector theorem. So what conclusion can you make about KJL in the diagram using the perpendicular bisector theorem? Well, this literally looks almost exactly the same. You could say that JK, just kidding, equals JL, just laughing, because point J lies on the perpendicular bisector of KL. So here's KL. This is the perpendicular bisector. It cuts it perfectly on the middle. K and L are equidistant. Therefore, the line segments are also equal. Hopefully that's clicking. There's your turn. Take a second. Pause before you let me do the work for you. Please have some integrity out there in the internet world. Suppose ED is 16 centimeters, okay? And DA is 20 centimeters. Find DC. Well, notice the tally marks. Notice that this is a perpendicular bisector. You know that this would have to be equal 20 centimeters because it would be just like the problem we did before. Take a look at EC. EC, no, yeah. EC is 15 centimeters. BA is 25 centimeters. Find BC. Well, clearly, this is equidistant from there, so you copy that over there. Follows the perpendicular bisector theorem, and that is the perpendicular bisector BD. So this would also be 25 centimeters. Sometimes geometry just feels like it's too easy, right? is what it is. So, explain 2. Good time to take a breath, pause, get your notes cleaned up. Next section, proving the converse of the perpendicular bisector theorem. Remember what a converse is, right? It's like the opposite. If P then Q, if Q then P. Not the shoes, although I am a fan of some Converses. The converse is also true. So in order to prove the converse, you need to use an indirect proof. That's a new vocab word in the Pythagorean theorem. Shout out your boy Pythagoras. Actually, I don't know. I don't know if he's a person worthy of shouting out as a human. I know mathematically he is. Some research on that. In an indirect proof, you assume the statement you're trying to prove is false. I'm going to say that again. In an indirect proof, you assume the statement that you're trying to prove is false. So think about how that could relate to something in your life to help you remember. You know, maybe like you're trying to, you've been accused of something, and you're trying to prove that that didn't happen. Then you use the logic to lead to a contradiction. So, anytime we talk about this stuff, I just think of a courtroom, right? I think of a detective, I think of a lawyer, and I think of them, playing mind games, getting people to trip up their words. So if you can get someone to contradict, using the information, definitions, postulates, or other theorems that you can then conclude that the assumption was false and the original statement is true. So that's wordy. Hopefully, as we go through this, it'll make a little more sense. Otherwise, my advice for all the geometry definitions is get it into your own words. I think that's the best thing you can do. So recall the Pythagorean theorem. It states that, for a right triangle, the legs squared, or the sum of the legs squared is equal to the hypotenuse squared. Legs, hypotenuse. Hypotenuse is directly across from opposite of the right angle and is the longest side length. So the converse, if a point is equidistant from the endpoints of a segment, so we flipped it, it's like thinking of it like a reciprocal almost, then it lies on the perpendicular bisector of the segment. So let's take a look at this example. We're given this diagram here. We want to know, well, we're given this, right? So PA is equal to PB. Now, looking at this diagram, that doesn't look to be the case, right? So, curious. So, the goal, prove P is on the perpendicular bisector M of AB. So, prove P is on the perpendicular bisector M of AB, okay? So, step A. I don't know why that's not called step 1. Assume that what you're trying to prove is false. It's kind of reverse logic, right? Assume that P is not on the perpendicular bisector M of AB. So it's not on there, which diagram kind of says that, right? Then when you draw a perpendicular line from P to the line containing A and B, so when you draw a perpendicular line from P to the line containing A and B, that's right there, it intersects AB at point Q, which is not the midpoint, right? So I hope you're kind of starting to see the setup. We're proving things that are not true. Step A is good. So not the bisector, not the midpoint. Step B, now complete the following to show that this assumption leads to a contradiction. Love contradictions. The line segment PQ forms two right triangles. Triangles AQP, and BQP. Alright, so now we got to pull out Pythagoras. So AQ squared plus QP squared is equal to PA squared. We with that? That's just applying the Pythagorean theorem. And now we know, if we can continue that logic, that BQ squared plus QP squared is equal to PB squared, right? PB squared by Pythagorean theorem. Alright, this is where you're going to do something that maybe isn't as comfortable. Subtract these equations. Treat it just like, in algebra, you combine like terms. So, what can we get rid of? So if you subtract these, that will cancel out. They go bye-bye. Santa, bye-bye. Or eggs or frogs if you're Yoda, baby Yoda. And then you get PA minus PB. So I'm going to write this over here just because I made it a little messy, and I really need to find a tablet that lets my... See, that's what was cool about the smart board, which I hate smart boards. That's a well-known fact. But they had that like magic handwriting tool, and I looked like I knew how to write. Alright, so PA squared minus PB squared. So let's take a look at that. Because we're saying that this would be on the perpendicular bisector, right? Those would be equivalent. So that would be 0. So then we're saying that these are equal. Right? Okay, so these would be equal 0. So we're saying that this now equals 0 because these two are the same. They cancel each other out. So this means that AQ squared would equal BQ squared. Obviously, this is where your algebra skills come in handy. You just move that over. So you get AQ squared equals BQ squared. Okay. Oh, it doesn't let me write out there. This contradicts the fact that Q is not the midpoint of AB. Thus, your initial assumption must be incorrect, and P must be on the perpendicular bisector. So that's a lot, right? And that's a lot to keep track of, and I know that's probably was a little confusing. But just know that you don't have, there's multiple ways to prove things, and sometimes proving things are not the way they seem, and then catching somebody up, again, go watch some crime shows, is how you do it. So if this were to be the case, this would have to be true. So therefore, we've just done it. So how can you tell that an indirect proof is used? Well, in the first step, you assume that what you're trying to prove is false. So if that's the tell there. A step that contradicts a known true statement means that the original assumption is false. So what you're trying to prove must be true. So again, lots of words. Write it out in your own way. Make sure you have the logical way that this makes sense. Once you know this, why can you conclude? Well, you take the square root of both sides, right? Obviously, and distances are non-negative. 7, your turn. Want to pause? Go ahead and do this for a second. So 80 is 10 inches long. BD is 6 inches long. Find the length of AC. So we're trying to find this. Well, let's take a look here. So D is equidistant, yeah? Therefore, that DB is perpendicular. So it is the perpendicular bisector. So DB is the perp bisector. Yes, of AC. Therefore, AC is 2. And how do we get that? Well, BC squared plus 6 squared. So BC squared, let me use a different color, BC squared, and that's your other leg, 6, and you're trying to find this, which we know, well, we're trying to find this, yeah? Yes, we're trying to find this one. We know that this is the same, this is 10. Gotta be careful. Do the math, we get BC squared plus 36 equals 100. Subtract 36 on both sides, you get 64. BC squared equals 64. Take the square root and you get BC equals 8. Therefore, AC has to be 16 inches. So that's the answer for 7. So figure out what you know, figure out what you don't know. Try to come up with an equation that allows you to find one unknown. If you have multiple unknowns in your equation, you're going to get stuck. You notice here I only had one, which is BC squared. Time to take a breath. Pause. Get a snack, and then come back. I'll still be here. Trust me. I'll be on YouTube until YouTube's not a thing. This video will live forever. Show it to your kids someday. Alright. So this is going to start tying in some of the things that we've been working on lately. So, proving theorems about right angles. So this symbol means that they're perpendicular. So L is perpendicular, line L is perpendicular to line M, or XY, the line XY is perpendicular to line AB. Prove each theorem. So if two lines intersect to form one right angle, they are perpendicular and they intersect to form 4 right angles. So given that measure of angle 1 is 90 degrees, prove the others are. Well, logically, you can assume that, right? Because if it's perpendicular, you know that they has to meet at a 90 degree angle, but let's prove it. Mathematicians must have just been bored, man. I guess back in the day they didn't have much to do. So, first statement given. Beautiful. Now look at this. That's claiming that we have a linear pair given. Well, knowing that, you know, the linear pair theorem states that if it's a linear pair, they add up to 180 degrees, so they're supplementary, and if one's 90, you do, you know, what they're talking about here, gets you the angle of 2. And then you can just continue to make connections. So 2 and 4 are vertical angles. Boom. 1 and 3 are vertical angles. Boom. Obviously, I skipped through the fun stuff here with the solving, but you should be able to see that if once you get one and you can find another pair, you keep rolling. No, that's the baby. Well, that's the middle baby. I don't know if you heard that. All right, let's take a look at B. If two intersecting lines form a linear pair of angles with equal measures, then the lines are perpendicular. If, then, if P, then Q. So that's what we're looking at. Make sure we are taking a look. So given, first measure of angle 1 is equal to measure of angle 2. Prove this. The line L is perpendicular to M. All right. Well, if these are equal, right, we know that they form a linear pair. And that's what it's saying, and that means they have to be supplementary. Linear pair equals supplementary. And that's by the LPT, linear pair theorem. I can't fit that in there. Not going to happen. So, therefore, they must add up to 180 degrees. And if you know that they're equal, because it was given, then you can replace, you know, measure of 2 with measure of 1 because they're the same. And you know that this is the SPE, subtraction property. I'm not going to sweat that, guys. Like, you can show it with, like, words if you don't need to get that in it. I feel like sometimes these solving steps to prove it so much can bog you down. So if you do that, you know that they're both 90 degrees. So 2 times that measure is 180, and they're just over the going here. Angle 1 is a right angle, and therefore, by the definition of perpendicular lines, purple is my favorite color. Obviously, every linear pair is supplementary, so if they're equal, half of that's 90 degrees. And you need to know that. Like, you just have to. Alright, so state the converse of the theorem in part B. Well, part B. So let's flip that around. If the lines are perpendicular, then two intersecting lines form a linear pair of angles with equal measures. Is it true? Yeah. So, flip that around. Your turn. Pause. Time to take a pause. Time to take a pause. Trying to do this. Really get comfortable with these diagrams, guys. So let's take a look. We're saying B is perpendicular. Parallel. B is parallel to D. C is parallel to E. We know the measure of angle 1. We know the measure of angle. Let me switch colors there. Angle 5. So 5. We know measure of 1. Find M4. Measure of angle 4. Okay. I like these things because there's just like stuff to do. There's stuff to do. But I don't want to do stuff I don't need to do. So, let's see. Okay, so let's start figuring out what we can. So we know this is here, right? Corresponding angles tells us that the measure of angle 2 is equal to measure of angle 1, so that's 50 degrees. We know that. Okay. Vertical angles tell us that measure of angle 3 has to be equal to measure of angle 2, which is 50 degrees. We're looking for 4. Let's not lose sight of that. And we know that angle 4 then has to be 40 degrees. And why? Well, this is a complementary angle, right? 3 plus 4, the measure of 3 plus the measure of 4 has to equal 90 degrees. And that leaves that to be 40 because that's 50. So, because the measure of angle 5 is 90 degrees, and this is 90 degrees, you can state that A is perpendicular to D. A is perpendicular to D. Yeah. I think that's really all you need to do. So this is clearly a linear pair. That could be the other way to do it, that this plus this equals, this plus this plus this equals 180. That equals 90 because the perpendicular. I think if I say more, I'm gonna make it confused. But take what you can, apply it down to the diagram. See, we didn't even touch up top, right? We just needed angle 1. So I think, yeah, I'm gonna stop talking because I feel like I'm just gonna confuse it. Don't gotta talk about that. Let's see, a couple questions to ask you guys. So let's talk about the essential question, and then we'll talk about the practice. So what are the key ideas about perpendicular bisectors of a segment? Well, if you know that a line is the perpendicular bisector of a segment, then any point on the line is equidistant from the endpoints of the segment. So turn that into your own friendly language, right? And if you know that a point on a line is equidistant from the endpoints of a segment, then the line must be the perpendicular bisector of the segment. So we know now that we can use that information because perpendicular means that it meets at a 90-degree angle, and that gives you more information about angle measures. So make sure that you really understand the theorem. Here's some practice. If there's anything with construction, I wouldn't trip. If you want to go for it, go for it. Definitely do stuff like this. Stuff like this with the diagrams. Yeah, I would mess around. Algebra stuff, clearly our guys are starting to see that you need your algebra here. These hot questions are always good to push yourself a little bit. Makes you think, makes you try to explain, which is what you want to do. So, well, y'all been asking for shorter videos, and I'm trying. 22 minutes I think isn't bad, because if we did this live or in class, it would probably take like 45 minutes. I think I did solid. I think you guys should be smooth. So 4.4 perpendicular bisectors, that's all the modules in this, or the lessons in this module. We'll hit some review, and then we just got 5 and 6. So may the force be with you, and do your work. I'll see you later.